Machine Learning, prepared by engineer Adil Saleh. Overview. Historically, computing relied on a strict bottleneck. A system could only perform tasks if a programmer wrote fixed, explicit rules for every single action. Machine learning, a prominent branch of AI, was designed to bypass this limitation entirely. Instead of following predetermined logic, ML algorithms are built to autonomously learn relationships by identifying recurring patterns within raw data. The defining characteristic of this system is continuous improvement. As the algorithm is exposed to more data over time, its performance automatically refines. The ultimate objective of mapping these patterns is to enable the system to make highly accurate predictions or decisions when it encounters new, unseen data. To understand how this form of intelligence operates, we will deconstruct its required system components and categorize its core learning models. Modern AI systems achieve intelligence by building algorithms that write their own rules through direct data exposure. Lesson sections. Every machine learning system, regardless of its end application, relies on a strict 5-part operational pipeline. This flowchart begins with data, the absolute bedrock of the system, originating from disparate sources like network logs, text, images, or sensors. From there, the pipeline moves to features, extracting only the relevant attributes from that chaotic raw data. Isolating these specific features reduces noise, which actually allows the algorithm to begin registering recognizable patterns. These features feed into the central model, the mathematical representation capturing strict relationships between inputs and outputs. Next is the training process. Here, the algorithm iteratively analyzes the data flow, adjusting its internal parameters. The single governing role of this training phase is error reduction, minimizing prediction errors. The ultimate quality of the resulting model is dictated by 2 factors: the sheer volume of training data and the operational effectiveness of this loop. The pipeline concludes with evaluation. The trained model is rigorously tested against unseen data withheld during the training phase. Evaluating on unseen data is mandatory. It proves the model has actually learned the underlying logic to predict future outcomes, rather than simply memorizing the training data it already processed. A machine learning model is only as capable as the strict pipeline that refines and tests inputs. The ML pipeline adapts based on the available data, determining the specific learning framework. The most common framework is supervised learning. This matrix illustrates the supervised learning architecture. It requires labeled data, meaning every input is explicitly paired with a known, correct output. The model learns the exact mathematical mapping function between them to accurately predict the future. Its primary applications are classification tasks, such as filtering spam emails and predicting continuous numerical values. The second major architecture is unsupervised learning. Deployed when fed entirely raw, unlabeled data, the algorithm is forced to independently discover hidden structures and similarities within the dataset. This structure is applied to complex clustering, dimensionality reduction, and massive-scale pattern discovery tasks. The choice between these architectures depends entirely on whether human operators provided a labeled answer key or tasked it to find its own order. A third learning model, reinforcement learning, focuses entirely on dynamic environmental interaction. This schematic shows the core mechanism, an autonomous agent taking concrete actions within an environment. This creates a feedback loop, issuing either a reward or a penalty back to the agent. Over time, the system learns optimal strategies purely to maximize its cumulative rewards. This is directly utilized in gaming, autonomous systems, and the physical actions of a robot. Executing any of these learning frameworks requires specific mathematical algorithms. The exact choice depends on the specific problem and the structure of the data. Standard foundational algorithms include decision trees, support vector machines, and k-nearest neighbors. This visualization represents neural networks, the ultimate algorithm for modeling extreme, high-variable complexity. They serve as the structural foundation for all modern deep learning systems. Whether navigating a physical environment or mapping labels, the underlying algorithm dictates the absolute limit of the system's processing power. These abstract models translate into a massive, real-world operational footprint across global industries. At an infrastructural level, machine learning executes disease detection and medical imaging in healthcare, fraud detection and market prediction in finance, and predictive maintenance in telecommunications. In the consumer sector, it powers speech recognition, natural language processing, computer vision, and the highly personalized recommendation engines driving platforms like YouTube and Netflix. Despite this widespread adoption, machine learning faces severe, unresolved operational friction. This chart outlines the primary challenges. The first logistical hurdles are massive data and compute requirements. Models demand extremely large datasets and require severe amounts of computational power to train effectively. There are also critical ethical and operational risks. Human bias can easily infect the training data, and researchers face the ongoing issue of model interpretability, understanding exactly how the machine arrived at its final decision. Guaranteeing fairness, transparency, and privacy within these opaque systems remains the most urgent area of ongoing machine learning research. As computational resources become exponentially more powerful and global data continues to scale, machine learning will stand as the central technology shaping future intelligent systems.